Let's now go back the other way, but we're not actually going to integrate inverse trig functions at this stage, but integration that will involve inverse trig, so the result will be inverse trig. In other words, it's the backwards of what we looked at yesterday. If I end up with an integral like this, then dx on the square root of a squared minus x squared, I know that's going to inverse sine, it'll be x on a. But what we also saw is, hang on a sec, it could also be minus the inverse cos. So we have a choice, depending on the question, which one we would end up choosing. The other one, where there wasn't a square root sign, so dx on a squared plus x squared, that went to inverse tan. But what we've got to be careful with this one is, out the front we do have 1 over a. The inverse sine one, we don't. To generalise that, if we want to create the integral by putting it in the form that we'd like to see. So if we see it in the form derivative over the square root of a squared minus function x squared, then that would be the inverse sine of function x over a, or of course the negative inverse cos of that same function. With tan, if we see derivative over a squared plus function x squared, again it has 1 over a out the front, the inverse tan of function x plus a constant. Let's do some examples. I see something like that. It's in that form of a squared minus x squared under the square root sign. That makes life easy. It's just inverse sine of x on 2. Over there, again, it's in the form that we like seeing, but remember, I'll have a third out of the front for this one because it's inverse tan. Let's do a definite one. We'll see these numbers come up a lot. They're things like 2, because it's going to create root 2 on the bottom, which will then allow us to have an exact value. So they tend to have those ones a lot. Doesn't mean it's always going to be like that. Substitute in 1, there it is, inverse sine of 1 on root 2, which we know is pi on 4, and inverse sine of 0, which is 0. So we get pi on 4 for our answer. One of these ones where, first of all, they ask us to differentiate something and then go and integrate. And there's a good chance then that what they're asking me to integrate is some multiple of what they just asked me to differentiate, or some combination of it with something else. In this case, let's differentiate it. Inverse sine, so the derivative, e to the x over the square root of 1 minus function squared, it in fact is exactly the same thing. Therefore, I know if I integrate, I go back to the inverse sine of e to the x. Substitute in the 0, remember with exponentials, be real careful. It is so easy to go, oh, I'm substituting in 0, and the inverse sine of 0 is 0. But remember, it's e to the 0, which is actually 1. So it's inverse sine of 1, now minus log 2. So e to the minus log 2, well, e to the log will cancel, but I need to get that negative sign back into the log. So it's e to the log to the 2 to the negative 1, which is a half. So we have inverse sine of a half, and we end up with pi on 3 for that one. So dx over the square root of 4 minus 9x squared. It's not quite in the form I'd like to see. I'd like to see the derivative of not 9x squared, but 3x, remember it's function x squared. The derivative of 3x is 3. I can easily put 3 on the top, multiply by a third out the front. It's now in the form we like seeing. So I know it's going to be 1/3 inverse sine 3x on 2. Okay, that's going back the other way.